So welcome everyone to the first technical session of REBLS. And Kento is going to talk about periodic and aperiodic task for FRP.
Thank you for introduction. I'm Kento Sogo from Tokyo Tech in Japan. Today, I will talk about periodic and aperiodic task description mechanisms in an FRP language for small-scale embedded systems. The objective of our research is to enable concise description and efficient execution of timed behaviors in an FRP language for small-scale embedded systems. To achieve it, we propose an extension of Emfrp, an FRP language. We introduce mechanisms for describing periodic and aperiodic tasks to Emfrp. The mechanisms include types for time-varying values that express their update timings and runtime system that executes periodic and aperiodic tasks efficiently. As a contribution, we can reduce power consumption and execution time by the runtime system. Here is the presentation outline. I would like to begin by discussing the background and motivation. First, I will explain Emfrp, an FRP language developed in our research group. Emfrp is an FRP language for small-scale embedded systems. The program on the left is a simple fan controller system written in Emfrp. This system measures temperature and humidity, calculates discomfort index, and determines the state of the fan from it. An Emfrp program consists of definitions of time-varying values. Time-varying values are called nodes in Emfrp. An Emfrp program can be represented as a directed acyclic graph with time-varying values as nodes and their dependencies as edges, like the figure on the right. Program execution can be viewed as continuously updating time-varying values along their dependencies. The execution cycle is called iteration. Now, I would like to talk about the motivation. Let's consider this system, a fan controller with two temperature sensors. Temperature sensors are located on the room's floor and ceiling. When the temperature difference exceeds 5, the fan is on. The fan is written like this in Emfrp. When the temperature difference is close to 5 degrees, even a slight temperature change can cause the fan to turn on or off, resulting in unstable fan operation. Therefore, some modification or improvement is necessary. Consider changing the code so that the fan is updated every 1000 milliseconds. This code seems good, but it has problems. We assume that iteration interval is dependent of time. If iteration interval is larger than 1 millisecond, clock ms may not increase by 1, and the exact time to update fan may be overlooked. Consequently, fan is not periodically updated. If iteration interval is smaller than 1 millisecond, the condition may become true many times in 1 millisecond, which would cause the fan to be updated too frequently. It is possible to describe it more precisely like this. Node fan timing represents the next update timing. When clock ms is greater than or equal to fan timing, fan is updated. However, this is a little complex. Moreover, even with the more precise description, reading from the temperature sensor is performed more frequently than update of fan. And then, power consumption increases. In summary, the efficient execution and precise concise description in MFRP are issues. I will now introduce a proposal to address these issues. We propose EVMFRP, an extension of MFRP. Language mechanisms to express periodic and aperiodic tasks include types for nodes that express their update timing, and operators regarding update timings such as merge, partialization, at now. Besides, EVMFRP provides runtime system to execute them efficiently. The concept of nodes in EVMFRP is different from the one in MFRP. The MFRP runtime keeps updating nodes repeatedly. So, nodes in MFRP are viewed as continuously time-varying values. On the other hand, nodes in EVMFRP are basically discrete. In EVMFRP, discrete nodes are updated periodically and aperiodically, and continuous nodes are obtained from snapshots of discrete nodes. Discrete nodes have their update timings as types. Timings of nodes are specified by timing annotation. For example, this code shows the declaration of I/O nodes. The variables TMP and HMD respectively represent temperature and humidity. Node temperature has a periodic timing 500, 1000. This implies that node temperature is updated 500 milliseconds after program start and subsequently every 1000 milliseconds thereafter. Node humidity has the same timing of temperature, and the timing of node fan is inferred by the EVMFRP processor. The motivative example discussed previously is described like this in EVMFRP. This code is more concise and precise description than that in MFRP. Next, let me explain features of EVMFRP. V at last n gives the value of a node V on n updates before. If at last n is applied to V, V must be defined with at least n initial values. This shows that temperature history has last 4 measured values of temperature, and a moving average is calculated using temperature history and at last. It's the same for humidity. Next, partialization is an operator that converts the timings of a node into a partial timing. Partial means, as shown in this figure, the original node always occurs at the same time when the partialized node occurs. This is an example program written in Emfrp. Fan controller. This system measures temperature and humidity every 1000 milliseconds and calculates moving averages of them using at last. The frequency of calculating discomfort index is reduced to 2500 3000 by the partialization operators. As node fan is dependent on node Ti and node Th, node Th is dependent on node fan. The Emfrp processor infers their respective timings to be 2500, 300. Let me explain a little more about operators. The merge operator generates a new time varying values from values with different timings. This operator requires two expressions and a function. As shown in this figure, when one of the expressions occurs and the other does not, the result is the one that occurs. When both expressions occur, it returns f, e1, e2. Next, v at now generates a continuous value from node v. V must have an initial value. While a discrete node cannot be referred to by a node with a different timing, continuous value can be referred to by any node. So at now is useful for handling nodes with different timings. A typical use case of the merge operator and at now is synchronization. By using the merge and at now in combination like this code, value with different timings can be synchronized. Discrete nodes can have aperiodic timings as well as periodic timings. The timing annotation of an aperiodic timing is represented as this. A node with an aperiodic timing is updated when the hardware interrupt corresponding to its label occurs. In this code, node PIR is defined with aperiodic timing PIR, and PIR will be updated when an interrupt of PIR sensor occurs. This is an example program using the merge operator at now and the aperiodic timing. This is a system with an LED and PIR sensor that uses infrared light to detect human. In this system, the LED turns on for at least 10 seconds after the sensor detects a person. Node LED is defined in this way. When node PIR time occurs, LED becomes true. After that, when timer time occurs and timer time minus PIR time is not less than 10,000, LED becomes false. Here, let me explain semantics of EVMFRP. Sequence is types for distinguishing the temporal properties of nodes. Each node is statically assigned one of the 4 sequences. This denotes first one denotes a discrete node with timing theta and L initial values. Second one denotes a continuous node which can be obtained by @null. Third one denotes a constant node, which is a node defined as a constant value. Final one is not assigned to a node intentionally. It is an error in type checking of sequence. We define the type system for sequences. The type judgment guarantees that nodes are updated at specific timings under the assumption that worst-case execution time is sufficiently small. WCET-aware compilation is a future issue. Let's move on to the implementation. We implemented a prototype compiler of EVMFRP. It generates 3 files: a C++ source file of runtime code, a C++ I/O code skeleton file, and a header. The I/O code skeleton is the platform-dependent part of a program. The developer needs to fill it in. It consists of 3 kinds of function: input function, output function, and initialization function. For example, an input function includes sensor measurement, and an output function includes output to GPIO. Initialization functions include device initialization, timer setting, and interrupt configuration. Next topic is memory management. A discrete node is managed by a ring buffer to enable retrieval of its previous value. It is compiled into an array with the number of initial value plus 1 element. A continuous node is compiled into a function as it is generated from a snapshot of a discrete node. A constant node is compiled into a constant variable. The runtime memory size is bounded. This is because, like MFRP, EVMFRP prohibits recursion. Next, let me explain how periodic tasks are handled in runtime. The time to process all periodic node updates in a program is controlled by one periodic timer interrupt. The occurrences of the timer interrupt must cover the occurrences of all periodic nodes. If a program consists of nodes with 2 timings, 500, 1500, and 1000, 2000, the timings of the timer interrupt is 500, 500. The runtime counts the number of times timer interrupt occur and decides which nodes should be updated. In this example, a node with 500, 1500 is updated on 1st, 4th, 7th interrupts. On the other hand, the time to process nodes with aperiodic timing is controlled by a corresponding interrupt. The compiler generates a function to update nodes at each aperiodic timing because we assume that an aperiodic event does not occur at the same time as other periodic or aperiodic events. This figure shows how to control periodic and aperiodic tasks. When an interrupt occurs, the interrupt subroutine sends its ID as a message to the event queue. We use free RTOS queue for the event queues. In the free RTOS task called the main task, a message is dequeued and identified which interrupt has occurred. And then the appropriate update function is called. This is how runtime works. Next, let's move on to the evaluation. We performed an evaluation of MFRP and EVMFRP for comparison. We measured program size, execution time, and power consumption. The program used in this evaluation is fan controller system. We used two boards, Arduino Uno compatible board and STM32 board. First, we measure the size of executable files compiled into for Arduino board. The result is depicted in this table. The text section is larger in EVMFRP because the runtime of EVMFRP depends on free RTOS library. On the other hand, the data and BSS section is larger in MFRP. We believe that the reason is because the MFRP compiler allocates runtime data except for primitive values in the static area. Next, we measure the execution time without I/O processing. We recorded the execution time for each iteration in MFRP and each update function processing per timer interrupt in EVMFRP. The difference between min and max is larger in EVMFRP. This figure explains the reason. Node DI is updated less frequently than temperature average. EVMFRP has advantage of eliminating unnecessary calculations. Finally, we measure the current consumption during execution. In STM32 nuclear board, we use wait for interrupt instruction. These figures depict the result. The EVMFRP runtime performs intermittently and saves power. Thus, the advantage of proposed method is that it can reduce power consumption in the interrupt standby state by using instructions such as WFI. That's it for our proposal. Next, I would like to discuss the related work. Here are some related work. Event-driven FRP is an FRP language well suited for interrupt-driven microcontrollers. Continuous time varying values behaviors change only when a discrete event occurs in EFRP. This semantic is similar to that of EVM FRP. Priority-based FRP is a reactive programming model. It originates from the FRP language that introduced priority to EFRP. The method of task scheduling is based on the abort and restart model, in which interrupted tasks discards its previous execution state and restarts from beginning. Synchronous language such as Estrel, Rooster, and Signal have been used to implement embedded and interactive systems. Some synchronous languages explicitly handle clock. In our work, the clock equivalent is introduced using types for nodes. Lastly, we would like to discuss the conclusion and future work. In conclusion, we propose mechanisms for describing periodic and aperiodic tasks and designed and implemented EVM FRP, an FRP language with the mechanisms. Besides, we performed evaluation experiments that shows that the proposed mechanisms realize efficient execution of periodic tasks on resource-constrained environment. Here is future work. First, as use of the operators, such as merge operator, can be confusing, language design needs improvement. Next, we performed evaluation using a simple program that only employs periodic nodes. Thus, we needed to evaluate based on practical scale application, including aperiodic tasks. Finally, real-time aware runtime design is also a future task. This is all for my presentation. Thank you.
Is there some question?
So I noticed you had some. Oh, sorry.
Sorry.
I noticed early that you had some kind of iteration. There we are. I noticed early in your slides that you had some kind of iteration. Is there a bound on that? Or did I misunderstand what I was looking at? I saw, so it was a directed cyclic graph as opposed to a directed acyclic graph. And I thought that you were suggesting that that suggested some kind of iteration, perhaps finding a fixed point. If not, then that answers my question as to how you can be real-time reliably. So, yeah, never mind. Sorry.
Can you hear me? Sorry, I'm not. So, excuse me, can I hear you? Question again?
I can try. Maybe slide 3 or so.
Is your question related, generally speaking, to data flow programming language?
Yes, there we are. So, did I guess correctly? No, it's 5. All right, so that iteration at the bottom, does that mean that there could be some interrelationship between the fan and the TH that would require iteration to cease or to... Sure.
Sorry, I can answer. So, okay, in this case, our language, so the graph of time varying value should be DAG, so no directed acyclic first. So, yeah, actually, so in this graph, so this is a, so dotted line. So this is a reference to the past value. So this does not affect. So I think how to say, the fan does only reference the current value of th, but the th had referred the previous value of fan. So this can be done in the
Yes,
without
that makes
any.
sense.
Okay.
Thank you.
A short one about your evaluation. Could you show us the slide? There is something that I have not understood. Next one, please. And again, the next one. Yeah, so I'm a little bit confused because for MFRP you say per iteration, and for EV MFRP you say per interrupt. So how do the two things compare?
Update function per timer interrupt is this includes counting the time of timer interrupt and identifying which node should be updated and updated nodes. So, and iteration is node updates. So
I don't understand your answer. Yeah.
Yeah. So the execution mechanism of MFRP and the EV MFRP are a bit different. So we just compare that one. So in MFRP case, it's just one iteration. This means that how much time to update all the nodes in the program. So the in case of EV MFRP, so we use per timer interrupt. That maybe correspond to. So can I have the previous slide? Okay. No, second graph net. This one. So yeah, this roughly correspond to the execution time for this time interrupt, and then do so, and update function for the node with periodic timing. So this in case of our setting, so without using aperiodic event, so that roughly correspond to the program that's the same. That's of the MFRP version. So that this requires update of nodes in that program. We just we just measure the execution time of this function. So that's the answer for you.
I also have a question, a clarification. Can you have a periodic task triggered by internal events? Or is it always from the outside?
Yes. Interrupt configuration is written in C++. In IO code skeleton. So you can write it in IO code skeleton and
But can you trigger a task, for example, when a Boolean goes from false to true?
Maybe it's possible. We have to
Yeah.
tested the kind of configuration.
Okay. Any other question? Thank you very much.
Thank you.